Hi everyone, thank you so much for joining us today for a guest speaker session. We have with us Dr. Seulki Part. Uh, she is a postdoctoral scholar at University of Michigan, and today she will be presenting her latest work that was presented at ICLEAR 2025. Thank you so much for taking out time, and I'll hand it over to you.
Okay. Thank you for the kind introduction and for having me here today. I'm Seulki, a postdoc at the University of Michigan working with Stella Yu. I'm excited to share our work, Visually Consistent Hierarchical Image Classification. So fine-grained classification has been a major focus in computer vision research. Typically, most methods are designed to predict a single, highly specific label, like Pembroke-Welsh Corgi for each image. This trend is driven by widely used benchmarks like ImageNet and iNaturalist, which contain thousands of fine-grained categories. However, does AI always need single fine-grained predictions? Sure, when possible, it's great to be that precise. A dog trainer or a pet owner might want to know the exact breed, like Pembroke Welsh Corgi, because different breeds have different temperaments, size, and behaviors. But however, that's not always necessary or even possible. For example, imagine an autonomous car driving at night. Suddenly, it detects something ahead on the road. It needs to quickly decide, is it a sign, a human, or animal? And if it's an animal, knowing it's a dog may be enough to trigger braking or swerving. The car doesn't need to know whether it's a retriever, a Maltese, or a corgi. In other words, in some situations, coarse-grained prediction is sufficient or even the only thing available. But in others, like dog training or medical care, we may need fine-grained predictions. So rather than forcing AI to predict a single fine-grained label, hierarchical classification aims to train a model to predict the full hierarchy from coarse to fine. So given an image, fine-grained classification predicts a single label at the most specific level. When the fine details are clear, as in this image, predicting just the fine-grained label may be enough, since the higher level classes can be inferred from the taxonomy. However, as we already observed, that's not always the case. For example, when a bird is flying high in the sky, it's nearly impossible to tell the exact species. In this case, fine-grained classification fails. It gives you nothing. But with hierarchical classification, we can still predict bird at a coarser level, which gives some valuable information. That's why we need hierarchical classification. First, it can adapt to different user needs, providing fine-grained or coarse-grained labels depending on what's relevant to the task. Second, it can still offer coarse but meaningful predictions when fine-grained details are unavailable. Hierarchical classification comes with two key goals. The first goal is multi-level accuracy, improving prediction performance at all levels of the taxonomy. But in practice, optimizing for both coarse and fine levels at the same time is challenging. They often compete with each other, and this can even lead to lower fine-grained accuracy than flat classifiers. The second goal is taxonomy consistency, making sure that predictions across levels follow the structure of the taxonomy. For example, if a model misclassifies a bird as ruby-throated hummingbird instead of green hermit, that's still within the same parent. So it's a reasonable mistake. But predicting something like arrowhead plant breaks the taxonomy. Such taxonomic inconsistency makes the output unreliable in practical applications. So to address these two goals, prior work typically uses separate classifiers for each level and supervise them independently with specific level-specific labels. Then they apply semantic consistency losses to encourage the predictions to follow a valid path in the taxonomy. In this figure, we show GradCam visualizations from a prior method. When predictions are correct and consistent, as in A, the coarse classifiers focus on the bird's full body, while the fine-grained classifier attends to the leg and tail regions that are semantically related. However, when predictions are inconsistent, like in this case, coarse classifiers looks at the bike's handle and frame, predicting motor vehicle, while the fine classifier focuses on a person's head, predicting feeder boa. The problem is the two classifiers rely on completely different visual cues because there's no guidance on where to look across levels. Thus, external consistency losses applied only at the output level is not enough to fix that. This is because predicting each level turns the problem into a multitask problem. For example, distinguishing between fine-grained species only needs local details like the color of the throat, but telling apart a bird and a plant requires more global features like overall shape. As a result, classifiers optimized at different levels tend to focus on different regions, leading to inconsistent predictions. For example, in this image, the fine level classifier correctly focuses on the bird and predicts as green hermit, but the coarse level classifier attends to the flower and predicts plant instead. So rather than only enforcing semantic consistency at the output, our idea is to align the internal visual reasoning across levels. We call this internal visual consistency. For example, at the fine level, the model might focus on the beak and tail, the parts of the birds, and as we move up the hierarchy, these parts are gradually grouped together into a full bird at the coarse level. This encourages all classifiers from fine to coarse to focus on semantically connected regions, ensuring consistent reasoning throughout the taxonomy. In summary, prior work enforces semantic consistency, but that alone doesn't fully prevent inconsistent predictions. We address this by encouraging all classifiers to focus on related visual regions so that predictions across levels are not just aligned in output, but also in how the model sees the image. Before moving on, are there any questions? Okay, if not, then let me explain our method. Our approach has two main components, visual consistency and semantic consistency. First, to enforce visual consistency, we leverage what we call internal visual parsing. And the idea is to segment the image into visual parts and ensure that these parts are grouped from fine to coarse in a way that aligns with hierarchical labels. For example, final segments are aligned with fine-grained supervision, while coarse groupings like the full bird are aligned with coarse level labels. This way, instead of having completely separate classifiers at each level, the model learns to make predictions that are visually grounded and consistent across the hierarchy. To achieve this internal visual parsing, we build and test a prior method from our lab published at iClear last year. Cast replace VIT patches with superpixels and uses a graph pooling module to perform bottom-up grouping from fine parts to coarse regions. Cast was originally designed to produce segmentation without any labels and for flat level, but we saw its potential to resolve visual inconsistency in hierarchical classification by grounding predictions at all levels in a shared visual structure. The second component is the three-path scale divergence loss. This encourages semantic consistency across the hierarchy. Specifically, we want the model's prediction to follow a valid path from the root to the correct fine-grained label. So instead of treating each classifier's output independently, we concatenate the logits from all levels into a single vector. We do the same for the ground truth labels. We concatenate the one-hot vectors for each level into one long target vector. Then we normalize the concatenated output so that it becomes a valid probability distribution. And we apply KL divergence loss between the predicted distribution and the target path distribution. This loss guides the model to predict a semantically valid path all at once, rather than just aligning each level individually. Uh, so these are all for our method. And do you have any questions? Okay, now let's move on to the results. So first, we show that HCast successfully learns fine-to-coarse visual consistency. This attention visualizations reveal that lower layers focus on fine details like face of the snake or the legs of the spider. As we move up the hierarchy, the attention gradually shifts to larger regions, eventually covering the entire object at higher levels. This shows that the model's focus is aligned across levels from fine to coarse, supporting consistent predictions throughout the hierarchy. And this validates our design from giving supervision from fine to coarse, because usually prior methods give supervision from coarse to fine in a taxonomy. And next, we show that HCast learns more consistent representations across levels. We evaluate this by comparing the nearest neighbors of each level's class token embedding. In this experiment, we compare our methods to higher VIT, a model that uses a standard VIT architecture with hierarchical supervision applied to each level's class token, but without internal visual parsing or three-path scale divergence. So this comparison highlights the effects of our contributions. Here, both models make correct predictions at both the coarse and fine levels. But when we look at the nearest neighbors, higher VIT retrieves a person in a black uniform as the fine level neighbor. This suggests the model may be focusing on appearance cues like black clothing rather than actual semantic identity of a dog. Even though it picks a dog at the coarse level, this mismatch reveals a disconnection between what the model attends to each level. In contrast, HCast retrieves the same dog at both coarse and fine levels, showing that its representations are not only accurate, but also semantically aligned across hierarchy. Let's see another interesting example from the last row. The input image is brown and white llama, and higher VIT selects a consistent pairs of samples across coarse and fine levels, but both are images of two brown cars standing on grass. So while the predictions are consistent, the fine-grained match is actually incorrect. This suggests that higher VIT may be relying on background cues such as green grass and brown color rather than the actual identity of the llama. In contrast, HCAST retrieves a fine-grained neighbor that shows both brown and white llama and a coarser neighbor that depicts a more general llama shape. This indicates that HCAST is capturing the true visual characteristics of llamas, learning features that are meaningful at each level of the hierarchy. Now let's look at the quantitative results. We evaluate our method on standard hierarchical classification benchmarks, and one of them is BREEZE, a two-level hierarchical dataset built from an ImageNet subset. It contains four distant subsets from living 17, non-living 26, entire T13, and entire T3. And the numbers here indicates the number of classes at coarse level and the number of classes at fine-grained level. And to evaluate hierarchical classification performance, we use several metrics, each capturing a different aspect of the task. And the most strict metric is FPA, full path accuracy. This counts a prediction as correct only if all levels are correct. So this measures both accuracy and consistency across the full taxonomy path. We also report level-wise accuracy at each semantic level, coarse and fine. And TICE, a metric that checks whether the prediction follows a valid path in the taxonomy. Even if some levels are incorrect, if the prediction follows a valid path, then it's okay. Across all subsets, HCAST consistently outperforms prior state-of-the-art methods, including both flat classifiers and hierarchical baselines. We also evaluate our method on a larger and more diverse dataset, iNaturalist. In the first table, it's on iNatural 2021, and it contains 273 course labels and then over 1,000 subordinate labels, and then 10,000 species fine-grained labels. And when we compare the results, HCAST outperforms hierarchical baselines by over 6% in full path accuracy. And also in the second table, it also outperforms fine-grained classifiers that use hierarchy labels to improve fine-grained label. So this shows the fine-grained accuracy. So these results demonstrate the effectiveness of our approach, combining visual grounding with three-pass supervision. These learn representations that are accurate and hierarchically consistent. Next, we compare HCAST to the large-scale vision foundation model CLIP. Even though CLIP is trained on hundreds of millions of image text pairs, our much smaller model predicts both coarse and fine labels correctly more often in a supervised setting. In particular, HCAST produces predictions that are both consistent and correct across levels. This orange shows the results of HCAST and blue shows the results of zero-shot CLIP. And CLIP often gets only the fine-grained label right, but fails at the coarse level. And we thought this was interesting because it suggests that CLIP is strong at distinguishing fine-grained categories using detailed visual textual cues, but weaker at recognizing higher level, like coarse-grained concepts that require structural abstraction. Our results show that explicit hierarchical supervision is necessary for helping models reason more reliably across the taxonomy, even when compared to large-scale pre-training like CLIP. Lastly, we show that HCAST also improves weakly supervised segmentation compared to the original CAST model. By leveraging hierarchy supervision alone and without using any pixel level labels, HCAST produces more semantically accurate segmentations. Uh, Now, let me wrap up by highlighting our key contributions. First, we present the first hierarchical classification model with internal visual consistency, which aligns model focus from fine details to core structure. Second, we introduce the new three-path scale divergence laws that encourages stronger semantic consistency across the hierarchy. Third, this combination of visual and semantic consistency leads to significantly higher accuracy and more reliable predictions across levels. And finally, our method also improves weakly supervised segmentation, even without using any pixel level labels, showing that hierarchical supervision helps in broader visual understanding as well. Together, these contributions show that structured visual grounding and taxonomy aware training can meaningfully improve both classification and segmentation. Um, I think it ends early, and thank you for your attention. And do you have any questions? Um, yes.
Hello.
Yeah.
Hey, again, thank you for your wonderful presentation. Can I ask something about the details of your model? Like, what backbone did you use for most of your experiments?
Okay. Yeah, we use VIT small model, and our model is our model uses backbone as cast, and cast also uses VIT small model, but instead of patches using in VIT patch is replaced with superpixel, and also there is one another module called graph pooling. So this is our model architecture. So we are using VIT. So in summary, we are using VIT small model, but patches are replaced to superpixel and graph pooling module is added.
Okay, so it's BIT small, and is it a pre-trained model or is it trained from scratch?
For Breeze dataset, where we use which is ImageNet subset, we trained from scratch. And for other datasets like iNaturalist or COB, we used ImageNet pre-trained model.
ImageNet pre-trained model. Okay. And just to make sure, so based on this figure, you use the features from the earlier layers to do the fine level classification and the features from the later layers for coarse level. Is that correct?
Um, Actually, that is first segments are so as byproducts, segments are produced, but we use supervision to the class token from each layer. So as shown in this figure, we gave fine-grained supervision at the lower level of class token, and we use coarse supervision at the finer layer of the class token. And we do not use the feature embedding explicitly. So we think it would be better to utilize features. And actually, we didn't include it on our yeah, we did include in our paper. We also had the ablation that we also used these features for training, for supervision, and it gave a little bit better performance, but it also made the model parameters, it increased the model parameters. So when compared to the increasing number of parameters, we thought the benefit is less. So that's why we only focus on class level class tokens. And we thought this was quite interesting because compared to simplicity of the supervision, the model internally processes this kind of visual grounding, and they implicitly help predicting each level labels. Does it answer your question?
Yes, I think so. Thank you. And one last question, because yeah, I'm not like that familiar with the super pixel idea. So when we think about super pixels and processing super pixels with a BIT, is it similar or analog to processing tokens? Because, well, from what I see, well, at the beginning, there seems to be more, these super pixels are more, well, fine, and then at the end, the super pixels are more coarse. So it's like working with a hierarchical feature extractor, kind of.
Okay. Thank you for the question. So we used off-the-shelf algorithm for generating superpixel like this, and it gave superpixel is kind of a very small grouping of pixels that are related to each other. So it gives the results like this. So every superpixel creation algorithm gives somewhat different results, but they are so in the paper cast, it also included the results using different superpixel algorithms. And so we are using that to generate superpixel. And then those, instead of, in VIT, they use the same scale patches, and we are replacing that with superpixel. And does it answer your question?
Yes. Again, thank you. Thank you very much, Dr. Park, for such a great presentation.
Thank you so much. Okay. Hiroshi?
Don't worry, it's okay. It's tough to pronounce. Thank you for the talk. It's really great. I wanted to ask like just two questions. One, I guess, is like a bit on ablation, and I was a bit curious, why did you choose graph pooling over any other like kind of pooling algorithm for your VT? Yeah.
Okay. First of all, graph pooling is yeah. Since our method uses backbone as cast, podcasts utilized graph pooling to uh, make visual groupings from fine details to coarse ones. So actually, we just followed and just adopt that architecture. But I agree with you that we could use another another pooling methods.
No, it's great. Like I was just wondering because it's like so specific. Like it's not often I see like graph anything graph related and within the transformers for multimodal stuff. That makes perfect sense. And then also I wanted to ask you, like you mentioned that so this is based on a vision transformer,
Mhm.
and you mentioned that you and the team compared it to Clip,
Mhm.
as in like performance, and you've outperformed Clip. And I was kind of curious in a way that, like you mentioned, the Clip is obviously bigger, but I was wondering, like, how big is HCast, from my understanding, like to compare it to Clip, like size-wise?
Okay, let me check. Let me briefly check because we included the number of model parameters in the.
Yeah.
If we don't
Okay.
have any other question, we can conclude the session.
Yeah. So this is okay. So we included the number of parameters, not for clip, but our model is about like 20 to 26 million parameters, and
Right.
BioClip, for example, has almost 150 million parameters.
Nice. Okay. Okay. Yeah. That's all for me. Thank you so much. It's great.
Thank you for casting. Yes.
Hi, am I audible?
Yes, I can hear you.
So I have a couple of questions. When you move from in your evaluations, since the data sets are, I mean, you have evaluated it on multiple data sets.
Mhm.
How skewed is your data set when you moved your labels from coarse to fine grain? And how did it affect training your model? That's my first question.
Okay. I couldn't catch that. Can you?
So I would want to understand whether the datasets that you have evaluated from when you moved from the coarse labels to the fine grained labels, is there any skewness? I mean, the skewness would have increased, right? Within the dataset.
Yeah. So, what do you mean by skewness?
I mean, for example, let's say if you have 10 classes in the coarse grain, then
Mhm.
let's say 500 classes in the fine grain.
Huh?
So the skewness in 10 could be, for example, let's say the first, there could be one top label, which is like occurring 50% of the times in the dataset. Okay, but there would be some labels which are like only occurring 10 times in the dataset. So how would that affect your model evaluation?
Okay. So, you mean the imbalance between?
Imbalance, class imbalances,
Okay.
and how does it vary from, because I'm not aware of these datasets, but I'm just asking if that does that have any impact on the HCAS performance if there is a class imbalance.
Okay. Actually, they are all class balanced.
Okay.
So yeah, we didn't have that problem in this setting, but I think that's also another interesting question, how hierarchical classification works in imbalance setting. Yeah, and as you said, that coarse label, since fine-grained labels will be accumulated to the number of coarse labels, so it will more accelerate data imbalance. So I think that will be very an interesting and realistic setting to work on.
Sure. Okay. So yeah, that's what I would want to understand in the evaluation if the data sets are. So the second question, I'm not sure if I'm framing it correctly, is that in I mean, I would want to first understand the motivation of the problem, which you have clearly mentioned in the beginning that when there are this problem, I mean, the primary reason for this hierarchical classification, for example, in your first slide, the very first slide, or I have seen in the paper also the paper, you mentioned that the Yeah. So here, can you move 2 slides a little? Yeah. So here, primarily the semantic consistency is primarily because there are two objects, the bird and the plant, which are closely related visually, right? So I would want to understand, let's say if these two, let's say if the bird and flower are, if you look at their visualizations, they're very close to each other. Let's say if they are very far, do you think the consistency would still remain same?
Mm, yeah, if I understood correctly, I think um, the motivation that we wanted to say here is that when we saw some more visualizations, we could observe that when there are multiple objects in the image, this kind of inconsistency has worsened. So that's why on Bree's dataset, which is ImageNet subset, usually they have more multiple objects compared to object-centric datasets like cop birds or aircraft-only images. So we thought that is why our method gained much more performance compared to other hierarchical classification methods, because on only one object-centric dataset like cop or aircraft, some hierarchical conventional methods performed better. And we thought that's because there could be less like visual structures that model needs to consider in those kind of data sets. And
Sure, sure. I got it. Thank you, and thank you for a wonderful presentation. Thanks.
thank you so much.